Welcome back. In this video, we are going to solve example 6.3 that is taken from chapter number 6, Bending, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. So statement is draw the shear and moment diagram for the beam shown. So you can see this is simply supported beam having a distributed load acting over the length of 18 feet, and we will divide this distributed load into a triangular load plus there is a rectangular load. So let's start with the solution. So first step is that if you remove this support, roller support at this point, let this is point 1. So we'll having reaction force which is R1, and if you remove this pin support at this point, let this point is point number 2. So you will be having a reaction force which is R2y, and there will be a horizontal component which will be equal to R2x. So we'll find this R1, R2y and R2x by using equation of equilibrium. But first we will divide this distributed load first into a rectangular load. So you can see whole this shaded portion is rectangular having magnitude of 2 kips per feet, and then there is a triangular load. You can see this blue color, this one is in triangular region. Let me draw it again. Okay, so this triangular is, now the magnitude here will be equal to 6 minus 2 will give you 4 kips per feet. Okay, and again we will divide, we will convert this distributed load when converted it into a point load. So it will be act at the middle, and this magnitude will be equal to 2 multiplied by the length over which it acts, which is 8. So that will be equal to 18, not 8, 18. So 2 into 18 is 36. This is 36 kip load. And this blue color triangular load when converted into a point load, so I will write it over here, it will be equal to 1 over 2 multiplied by this 4 and the length over which it acts, which is 18, and that will act at a distance of L by 3 from this side. So L is 18, so 18 by 3 is 6 feet. So 6 feet from this side and 12 feet from this side. Okay, and the distributed load, since it is acting at the mid, so it will be at a distance of half of the 18, which is equal to 9 feet. Now we can apply the equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force toward right is taken as positive. So from this you can see only the horizontal force which is R2x is acting. There is no other force, so it means that R2x is equal to 0. Now we will find the second force by using equation of equilibrium, that sum of all moment about point 2 is equal to 0 and taking the counterclockwise moment as positive. So about this point 2, first moment will be this R1 into perpendicular distance is 18, and this is producing clockwise movement, so it will be negative. So I can write it as minus R1 times 18. The second force that is producing movement is this 2 into 18, and perpendicular distance will be this one, which will be equal to 9 feet. And this is producing counterclockwise movement, so it will be positive. So I can write plus 2 multiplied by 18 into 9. The last force that is producing movement about point 2 is this force multiplied by perpendicular distance is 6, and this is also producing counterclockwise, so it will be positive. So I can write plus 1 over 2, 4 multiplied by 18 into perpendicular distance 6 is equal to 0. Now we will get minus 18 R1 plus 2 multiplied by 18 multiplied by 9 is 324. So 324 plus 4 into 18 multiplied by 6. 4 into 18 multiplied by 6 divided by 2 is 216 is equal to 0. So 324 plus 216 plus 324 is 540. So it means that 18R1 is equal to 540. So if you divide this answer by 18, you will get 30. So from here R1 is equal to 30 kip. Now you have this R1, so we will find this R2y by using the third equation of equilibrium, that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see R1, which is plus minus this 36 minus this 4 multiplied by 18 divide by 2 is 36. It is also 36. So minus 36 plus R2y is equal to 0. So from here you will get this 30 minus 36 minus 36 is 42 minus 42. So R2y will be equal to 42 kips. Now you have all these three reaction forces. So what we will do is that if I copy this diagram over here, let me copy it and I will paste it over here. So you can see that if I section it at a distance of x, at any distance which is x, let me call this distance as x, and x is greater or equal to 0 and less or equal to 18 feet. And if I draw the free body diagram, so it will be like this. Let me draw it first here at this is your point 1 where you have R1 and R1 was 30 kip, and this distance where we cut the beam is x. Clear? And you can see you have a distributed load plus a triangular load. So this distributed load is 2 kips per feet. And what about the distributed load over here? Since we have 6 feet or a length of 18, so if I take 6 divided by 18, that will be equal to W divided by X. So from here we will get this W is equal to 6 by 18 multiplied by X. Okay, not 6, sorry. This was, the remaining was 4 kips. So correct it. So this is 4 feet. Let me take it. This was 4 divided by 18 divide is equal to W by 6. So 4 by 18. So we will get W will be equal to 4 by 18 into X. Okay. So what we will do is that we will convert this distributed load into a point load. So it will act at the middle of this beam, and that will be equal to 2 multiplied by the length over which it acts, and the length is X. Now here W is equal to 4 by 18 times X. So when this triangular load is converted into a point load, so it will be equal to 4 into 4 by 18 into X. This is the magnitude, so 1 over 2 into magnitude, and the X is the length over which it acts. So when you cut it, you will be having a shear force V, as well as you have a reaction moment at the section where you cut it. Okay, this is M. So we'll find this V and M by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see 30 kips is upward. So 30 minus this 2x which is acting downward, so I can write minus 2x minus this load which is 1 over 2 multiplied by 4x square divided by 18. Clear? That is minus v is equal to 0. So as we are interested to find out v, so v is equal to 30 minus 2x, and this term 2 will cut with this 4, so 2x square over 18, so it will give you x square over 9, and the unit of this equation will be in kip. That this is your equation number 1. Now we'll find this m by using equation of equilibrium, that sum of all moment is equal to 0 and taking the counterclockwise movement as positive. Since we are taking it at a point and that is 1, so we will take sum of all the moment about point 1 is equal to 0. So starting with the first load, which is 30 kips into x, about point 1 is producing clockwise movement, so it will be negative. So I can write minus 30 into x. The second load which is producing movement is 2x, and since this is a point load due to this distributed load, so it will act at a distance of x by 2 from this point 1, and that is producing counterclockwise movement, so it will be positive. So I can write it plus 2x, and perpendicular distance is x by 2. Let me write the perpendicular distance for that. This distance is x by 2, and for this triangular load, this distance will be equal to x by 3 from this side. Okay, the last load that is producing movement is this load, and perpendicular distance is x by 3, and this is also producing counterclockwise movement, so it will be positive. So I can write it plus 1 over 2 4 by 18 times x into x, and perpendicular distance is x by 3 is equal to 0. Okay, not 0. We have left the one term which is this moment term. You can see, and this counterclockwise movement is taken as, and their sum must be equal to 0. So from this we will get movement will be equal to 30x minus x square, and this 2, it will be 2 will cut with this, so 9 minus x cube over 3 8. Okay, x by 3, so it will be 2 into 9, and 3 9s are 27, and this will be the moment equation, and the unit will be kips into feet. This is your equation number 2. If you want to check whether equation number 2 is correct or not, so we know that this shear force is equal to dm over dx. So if you take derivative of this equation, dm over dx, so it will be equal to 30 minus 2x minus 3x square over 27, which will give you 30 minus 2x minus x square over 9, and that is equal to shear force, and which you can confirm from equation number 2. These are same, so it means that your equation of the second equation number 2 for the moment is correct. Now moving to draw the shear force and bending moment diagram, what we will do is that we have both the equation, so we will draw a vertical line from the end of these beams, and first we will draw the shear force and then bending moment diagram. So for that I am drawing a horizontal line that show you x in feet, and on y-axis you have shear force having units kips. Okay, let we take one division is 15 kips, two division is 30 kips, third division is 45 kips. There similarly minus 15, minus 30, minus 45. Okay, starting with this equation number 1, I will take the help from the calculator. So if you want to solve it, so you have to go to the table, you have to write the equation. The equation was 30 minus 2x minus x square, x square, square divide by 9. Okay, so this is the equation, and we will put the value of x is 0 and the second ending value is 18 feet. 18 feet, and we will go in one step. So you can see, okay, so you can see at x is equal to 0 you have 30, and at x is equal to 18 you have minus 42. You can check it for x is equal to 0, and you can get different values. At x is equal to 127.88, at x is equal to 225. So you have all these values, you can just plot it. I will draw direct 2 points and we will see what we will get. So at x is equal to 0, at x is equal to 0, put in equation 1, we will get v is equal to 30 kips. And at x is equal to 18 feet, put in equation number 1, we get v is equal to minus, let me check it, minus 42 kips. 42 kips. Okay, so for plotting, first we will plot at x is equal to 0. We have first point is this one, and at x is equal to 18. So we have minus 42 kips. Okay, now you can see that we do not know in between these 2 points. We know that our shear stress will be 0. That is in between 9 and 10. The shear force comes down towards 0. So for finding that, for x at which shear force is 0, so we will take this equation 1 equal to 0. So this is equation 1. So v is equal to 0 is 30 minus 2x minus x square by 9. So rearranging it, we will get minus x square by 9 minus 2x plus 30. So by using calculator, we will solve this quadratic equation. So go to the mood, then go to the solve the polynomial degree 2, and then just put the value of this minus 1 divided by 9 is the value of for A. For B we will have minus 2, and for C we have plus 30. So when you solve this, you can see x, one of the root is 9.734 and the second is minus. So we will neglect the value. So we will choose the one root. X will be equal to 9.735 feet. Okay. So at this point, we will see that what is the value of this shear force. So at x is equal to 9.735 feet, we will choose this, put in equation 1, we will get v is equal to 0. Now by using these 3 points, one is this one, second is this one, and third is this one. So we will draw the shear force equation. So v is equal to 0 at 9.735. So let 9.735 is there, 9.735. So again you can see this loading, distributed load is the combination of this uniformly distributed load and triangular load. So we will get the curve like this. It will be not a straight line, but it will be like this. and from this you will move in curve form. Okay, so this is your shear force diagram. This distance is 9.735 feet at which shear force is equal to 0, and that is shear force diagram. Now we'll move toward the bending moment diagram, and for bending moment diagram I will draw a horizontal line for x in feet, and on y-axis you will have a moment, and let each division is 50. So 50, this is 100, this is 150, and this is 200. Okay, we have the equation for the moment is this one. You can see this moment equation is, so for we will find for moment x is equal to 0. So if you put this x is equal to 0, so all the term will be 0. So we will get moment will be equal to 0. And for x is equal to 18 feet, put in equation number 2. So when you will put it in equation number 2, you will get this moment will be also equal to 0. And at x is equal to 9.735 feet. So when you put it in equation number 2, so you will get moment will be equal to 163 kips into feet, and that will be the maximum bending moment. Why this is maximum? Because the region at which shear force will be equal to 0, you will get the maximum bending moment. So plotting this point at x is equal to 0, you have moment is equal to 0, and at x is equal to 18 feet, you have moment is equal to 0. And for x is equal to 9.735, we have moment is 163. Let this point is 163 kips into feet. So if you plot it, it will be a curve like this, clear, and you will get a curve like this, which will be your bending moment diagram. So this was all about this example 6.3. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 5.25 that is taken from chapter number 5, Analysis and Design of Beam, and the book name is Mechanics of Material, Beer and Jhonston, 6th edition. So statement is draw the shear and bending moment diagram for the beam and loading shown. Determine the maximum normal stress due to bending. So you can see this is an overhanging beam AB having roller support at point C, and at point D you have pin support. At A you have a 5 kips load, and at D you have 10 kips load. And this is wide flange beam W14 by 22. So you have to determine the shear force and bending moment diagram and determine the maximum normal stress. So I will write first what you have to find is that in part first, determine or draw the shear and bending moment diagram, and in part B you have to find the maximum normal stress due to bending, which is sigma max. Clear? So let's start with the solution. So what will be the first step is that if you remove this roller support at point C, so you will be having a vertical reaction force which will be represented as C, and if you remove this spin support, so you will be having a vertical reaction force B. There will be a horizontal reaction force Bx as well, but you can see there is no other force, so Bx will be equal to 0. So we will find this C, B and Bx by using equation of equilibrium. So first equation of equilibrium is this one, and only Bx is acting, that is in negative direction, and there is no other force, so it means that Bx is equal to 0. Now we'll find this Cy by using another equation of equilibrium, and that is sum of all moment about point B is equal to 0 and taking the counterclockwise moment as positive. So you can see about point B, the first moment is due to this 10 kilonewton load and perpendicular distance is 5 and it is producing counterclockwise movement, so it will be positive. So I can write it 10 multiplied by 5. The second moment is due to this C and perpendicular distance is 13 and this is producing clockwise, so it will be negative. I can write it minus C into 13. And the last moment that is produced due to this 5 kilonewton and perpendicular distance is now 18 and it is producing counterclockwise movement, so it will be positive. So plus 5 into 18 is equal to 0. So this will give us 50 minus 13 times C plus, I will check, 5 multiplied by 18, which will be 90. So 90 plus 90 is equal to 0. So 90 plus 50, so 13C is equal to 140. So 140 divided by 13 will give us 10.76. So from here, C will be equal to 10.76. Okay. Now you have this C, so you can find this B by using the third equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So minus 5 kips plus C, so minus 5 plus C is 10.76 minus 10 plus B is equal to 0. So you can see minus 15 plus 10.76 plus B is equal to 0. So we'll choose the calculator. Minus 15 plus 10.76 will give you minus 4.24, and when it will go toward the right hand side, so it will be 4.24. Okay, sorry, B will be equal to 4.24. Okay, now you have all these reaction forces, so we can easily move toward shear force and bending moment diagram. So for that, what I have to do is that I have to take the vertical lines from the end of this beam clear in order to draw the shear force and bending moment diagram. First, I will draw a horizontal line to show the x is in feet, and on y-axis you have V, which is shear force, and unit will be kips. Let me take one division is equal to 2 kips, so 2 to 4, you can take it by your own as well. So minus 2, minus 4 and minus 6. Okay, starting from the first point, you can see at point A you have minus 5 kips load. So this will go toward downward. So our first point will be this one, minus 5 kips. As you can see that moving from A to C, there is no other load, so it will remain horizontal till this point C. So what I will do is that I will mark these points. This is your point C and this is your point D. Okay, so from this till point C, we do not have any load, so it will remain same. Now at point C, you have plus C, which is 10.76. So minus 5 plus 10.76 will give you how much? Let's check it. Minus 5 plus 10.76 will give you 5.76. Okay. So this will be the point. Let this is the 5.76 kip. Okay. So shear force will change from minus 5 to plus 5.76. Now moving from C to D, there is no other force, so it will remain horizontal till this point D. And at point D, you can see you have minus 10 kips load. So minus 5 plus 5.76 minus 10 will bring it to minus 4.231. Let me check it. 5.76 minus 10 is 4.24. So 4.24 will be somewhere here. It will be like this. Okay. So shear force will change from this to this point. and from D to B there is, you can see there is no other force, so it will remain horizontal till this point, and at point B this is minus 4.24, and at point B you can see you have plus 4.24, which will bring it toward the 0 and will complete your shear force diagram. Moving toward the bending moment diagram, so again I have to draw a horizontal line to show the length x in feet, and on y-axis you have moment that is having unit kips multiplied by feet. Okay, let's take one division is equal to 10. So this is 10, this is 20, this is 30. You can take as per your own requirements, minus 10, minus 20, and minus 30. Okay. Starting from first point at A, you can see you do not have at x is equal to 0, so bending moment will be 0 at this point. Now we can see that area under the shear force diagram will give you bending moment. So first area under the shear force diagram will give you bending moment. Let me call this area is A1. So I will write here A1 is equal to minus 5 multiplied by the length over which it x is 5. So it will give you minus 25. So at point C, C is this point. So this will be minus 25. So which will be like this. This is minus 25. And you can see that shear force is a horizontal line and this A1 area is negative. So bending moment will be 1 degree line and slope will be decreasing. So it will be like this. I will join these 2 points using straight line. Okay. Now the second area under the shear force diagram is this one, and you can see that A2 is equal to 5.76 times 8. This distance is 8 feet. So 5.76 multiplied by 8 will give you 5.76 multiplied by 8 is 46.08. 46.08. Now minus 25 plus 46.08 will give you overall minus 25 plus 46.08 will give you 21.08 moment at point D. 21.08. So 21.08 will be somewhere here. This is your point. It will be somewhere here. Let me write it 21.08. And you can see that shear force is a horizontal line with area A2 is positive. So bending moment will be 1 degree higher and it will be a straight line. Slope will be increasing. Now the last area is A3 and you can see A3 is equal to minus 4.2324 multiplied by 5. So I will choose minus 4.24 multiplied by 5 will give you 21.2 minus 21.2. Okay, I think we have made a mistake. This will also give you A2 will also give you minus 21.2. Okay, what is E2? E2 is 40. Let me check it. 5.76 multiplied by 8 is 46.08 minus 25 is 21.08. Okay, and this is minus 21.2. Okay, now 21.08 minus 21.2 is equal to 21.02 minus 21.2 is minus 0.18. So it means that this is negative, so it will be approximately equal to 0. Clear? And you will get the point at, and it will be this one. Now you can see that shear force is a horizontal line and area A3 is negative, so bending moment will be 1 degree line and the slope will be decreasing. So it will be like this. So this is your bending moment diagram for the beam and this is your shear force diagram. Okay. Moving toward part B, in part B we have to determine the maximum normal stress. So we know that maximum normal stress is equal to absolute value of maximum bending moment divided by section modulus. And From this shear force bending moment diagram, you can see that maximum bending moment is 25 kilonewton into meter. So maximum absolute value of bending moment is minus 25. I can write it maximum absolute value of this bending moment is minus 25 mod, which will give you 25 and unit will be kips into feet. Converting this feet into inch, so I can write it at maximum absolute value of bending moment is equal to 25 kips multiplied by 12. 1 feet is 12 inch, so it will be kips into inch. So 12 multiplied by 25 will give you 300. So it will be 300 kips into inch. Okay. Now what about section modulus? So we have been given 14 by 22. So what we will do is that we will move from appendix C, section property, and we will get the S for W 14 by 22. Okay. So let's go towards the book. This is the book. You can see you have to go at the appendix C, and in appendix C, property of rolled steel. So you will go, now you can see this is US customary. Okay. So in US customary, you can see this one is W. So W 14 by 22. So this is the last one is W. I cannot use the pen over here. Why? Okay, yes, this is okay. Editing is unavailable. So you can see the last one is W. This is 22. So your this value will be 29. You can see this value is 29, which is for SX, and unit will be cubic inch. So SX or S will be equal to 29 cubic inch. Now you have all the values, so just can put it. Maximum bending stress is equal to absolute value of maximum bending moment divided by section modulus, which is Sx. So you can write 300 kip into inch divided by 29. So 300 divided by 29 will give you 10.34. Sigma max is equal to 10.34, and unit will be kip per square inch, and kip per unit per square inch is also known as KSI. Kilo pound per square inch. And this is the answer of our second part. So this was all about this problem 5.25. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. In this video, we are going to solve problem 5.10 that is taken from chapter number 5, Analysis and Design of Beam, and book name is Mechanics of Material by Beer and Jhonston, 6th edition. So statement is draw the shear and bending moment diagram for the beam and loading shown and determine the maximum absolute value of shear and bending moment. So you can see this is a cantilever beam having fixed support at point B, and from A to C there is a distributed load of 2 kips per feet and point load of 15 kips at point D. The total length of this beam is 12 feet. So you have to draw the shear and bending moment diagram, and then you have to determine the absolute value of maximum shear and maximum bending moment. So let's start with the solution. We will solve this problem by using two methods. First one will be the direct method. So I will write it method 1, which is very easy, clear, and after that we will solve it by using second method, that is first we will find the shear force and bending moment equation. Okay, starting from method 1, if you remove this fixed support at point A, so that will offer a reaction force which will be represented as B, y, as well as there is a horizontal reaction force which is bx, and there is a moment which will be like this reaction moment which will be mb. So we'll find this mb, bx and by by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force toward right is taken as positive. So you can see only bx which is acting horizontally and there is no other force, and this is in negative direction, so it means that minus bx is equal to 0, and from this we get that horizontal reaction force bx is equal to 0. Now we'll find the second reaction force by using another equation of equilibrium, that is sum of all movements about point B is equal to 0 and taking the counterclockwise movement as positive. And we know that from A to C there is a distributed load, and this distributed load when converted into point load, so it will be 2 times the length over which it acts. So 2 multiplied by 4, and that will be equal to 8 kip. Okay, and that will act at a distance of 2 feet from both sides, either from C or from A till the mid. Okay, so this is 2 feet and this is 2 feet. Now we'll apply this equation. So first force that will produce movement about point B is this 15, and perpendicular distance is 4 feet, and it is producing counterclockwise movement, so it will be positive. So I can write it 15 multiplied by 4, that is positive. The second moment is produced due to this 8 kips load, and perpendicular distance is now 10 feet, and it is also producing counterclockwise movement, so it will be positive. I can write it plus 8 multiplied by 10. And the third moment which is producing which is the reaction moment mb, that is clockwise, so it will be negative. So minus mb is equal to 0. So from here we will get mb will be equal to 60, 15 multiplied by 4 is 60 plus 80, clear, and that will give you 140, and unit will be kips into feet. So we get this reaction moment mb is equal to 140 kips multiplied by feet. The last thing which we will find is by, and that we can find it by using third equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see 8 kip is downwards, so 15 is also downwards, so minus 8 minus 15 plus by is equal to 0. So I can write it plus by minus 8 minus 15 is equal to 0, and from this we can get that by will be equal to minus 20 plus 23, because by minus 23 will be equal to 0 and by will be equal to 23, and unit will be kip. Now we have all this reaction force, so we will find the shear force and bending moment diagram. For that I have to draw the vertical line from the end of this beam, just like here I will draw, clear. The first thing that we will find the shear force diagram. So again for that I have to draw horizontal line and to show length in feet. Okay, on y-axis you have shear force having unit kips, clear. Let take one division is equal to 5. So 5 kips, so it will be minus 5, minus 10, minus 15, minus 20, and minus 25. Okay, starting from the very first point at point A, you can see shear force is equal to 0 because there is a distributed load. So for x is equal to 0, so 2 multiplied by 0, it will be 0 at this point. So first point will be this one, clear. Now we are going to find out the shear stress at point C. This is point C and this is your point D. Okay, and this is your point B. So at point C, it means that at x is equal to 4 feet. 4 feet. This load will be equal to 2 multiplied by 4, which is 8, and that will be minus 8 because the load is downward. So at x is equal to C, or at C we have minus 8. So let minus 8 is here. You can write it minus 8 kip. Okay. Now you can see that the distributed load is a horizontal line with 0 degree, and that is downward negative. So shear force will be 1 degree higher. It will be a straight line, but slope will be decreasing. So it will be like this. Now moving from C to D, there is no load, so this shear force will remain same till point D. But at point D, you can see you have minus 15 load. So minus 15 and minus 8 will give you minus 23 kips. So shear force will change from minus 8 to minus 23. So let's say minus 23 is somewhere here. This is your minus 23. Okay. So shear force will change from this to this. And again moving from D to B, there is no other shear force. It will remain same horizontal. And at the end, you can see you have By, which is plus 23. So minus 23 plus 23 will give you 0. So this is your shear force diagram. Clear? And we will now move toward bending moment diagram. So for bending moment diagram, again, what I have to do is that I have to draw a horizontal line to show x in feet. And on y-axis, you have movement that will be kips into feet. Okay. Let we take 1 division is equal to 25. So 25, it will be minus 50, minus 75, minus 100, minus 150. Okay. Or 125, sorry. 125 and minus 150. You can take as per your own requirement as well. Okay. Now what we will do is that you can see that area as area under shear force diagram gives you bending moment. So we will do that. We will take the first area under the shear force diagram is this one, from A to C. From C to D is like this, and from D to B, the area under the shear force diagram is this. So we will split them into 3 areas. This will be your first area A1, which will be this one. The second area will be A2, and third area will be this one. So first we will calculate A1. So A1 is how much. You can see this is um, a right angle triangle, so its area will be 1 over 2. Its base is 4 feet, and height is minus 8. So I can write it as 1 over 2 minus 8 times 4. And when you calculate it, it will be minus 16. Okay. This is area for region A to C. This is your point A. Okay. Now we will find A2, and A2 will be equal to how much. You can see this is a rectangle. So this will be, height is minus 8 and width is 4 feet. So minus 8 multiplied by 4 is equal to minus 32. And this is for region C to D. The third thing we will find is E3. So E3 is again rectangle. So you can see this height is minus 23 and width is 4. So minus 23 multiplied by 4 will give you how much. We have a calculator. 23 multiplied by 4 is 92. Minus 92. And this is for region D to B. Now you have all these areas. So let's start plotting all these points. So at point A, we have movement is equal to 0 because x is equal to 0. Now this area, this is your point C, this is your point D. So area under the AC region is A1, which is minus 16. So first we will plot minus 16. So let's say minus 16 lies somewhere here. Clear? So you can see that shear force is a 1 degree line, straight line, and slope is decreasing. So bending moment will be a curve, and it will be like this, clockwise direction. Now the second area, this is minus 16, this at this point. Now From region C to D, the area is minus 32, but at point D, we will have the total bending moment will be equal to A1 plus A2, and that is equal to minus 16 and minus 32, which is equal to minus 48. So we will plot minus 48. So let's say minus 48 is this point. Again, you can see that you have a shear force is a 0 degree line with a negative area. So bending moment will be a straight line, but the slope will be decreasing. So we will join these 2 points using straight line. And the last area is A3, which is how much? Minus 92. So at point B, the total area will be equal to A1. Our total bending moment will be A1 plus A2 plus A3. So A1 plus A2 is minus 48 and A3 is minus 92. So that will give you 140, minus 140. So at the end, we will have minus 140. So let's say minus 140 lies somewhere here. Okay. You can see that shear force is a horizontal line with 0 degree. So bending moment will be 1 degree higher. It will be a straight line, but slope will be decreasing. So we will get this point. And at the end, you can see you have this moment MB, which is how much? MB is plus 140. So it will bring back it to point 0. So this will be your BMD, bending moment diagram. So we have drawn the shear force and bending moment diagram. Now we will determine the maximum shear force and maximum bending moment. So for a second part, in part A, we have to determine the absolute value of maximum maximum shear force. So you can see here the maximum shear force is 23. Clear? So I can write V max absolute value is equal to minus 23, and that will be equal to 23 kip. And for B part, we have to find the maximum absolute value of bending moment. And from this diagram, you can see the maximum absolute bending value is 140. So I can write it maximum absolute value is minus 140 mod, and that will give you minus 140 kips into feet. And which is the answer of our second part. Now we will solve the same question by using another method that will be using shear force equation and bending moment equation. So in method 2, I will write method 2, and the method is by using shear force equation and bending moment equation. Once we get the shear force equation and bending moment equation, then we will draw the shear force and bending moment diagram. So what will be the first step? You can see you have 3 regions from A to C, from C to D, and from D to B. So we will take the region. First we will take region A to C. Now A to C means that X is greater than 0 and less than 4 feet. So this is the region A to C. Okay. So what we will do is that we will cut this beam at a distance of X, where X greater than 0 and less than 4 feet. And we will draw the shape free body diagram. So it will be like this. This is your point A. This is the distance where you have cut the beam. This distance is represented as X. Clear? And there is a distributed load over a length of this X. And the magnitude of this distributed load is given by 2 kips per feet. Okay, so when you cut it at this point, so you will be having a shear force which is acting downward V, and you will be having a moment M. And let we call this point as point J. So we'll find this M and V by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. Okay, you can see you have a distributed load. So when this distributed load is converted into a point load, so it will be equal to 2 multiplied by the length over which it acts. So length is x, and it will act at a distance of x by 2 from both sides, from either side. So this distance is x by 2. This is also x by 2. Now we will apply this equation. So you can see the sum of all forces along y direction must be equal to 0. So 2x which is acting downward. So minus 2x minus v is equal to 0. So it means that v is equal to minus 2x. Minus 2x. And unit will be kept. Now when you put the value of x for different x value that is defined over here, x is greater than 0 and less than 4 feet, you will get the value of shear force for the region AC. Again, the moment M can be obtained by using sum of all moment about point J is equal to 0 and taking the counterclockwise moment as positive. So about point J, the first moment is due to this 2x and perpendicular distance is x by 2 and it is producing counterclockwise moment, so it will be positive. And the second is reaction moment, which is also counterclockwise, so that is also positive. So we can write plus m plus 2x into x by 2 is equal to 0, and from here we will get this moment will be equal to x minus x square, and the unit will be kips into feet. Now this is the moment for the region AC. Okay, now at x is equal to 0, put it in this shear force equation. So you will get VA is equal to 0. And if you put it in this moment equation, so moment MA will be also equal to 0. So this is the value of shear force and bending moment at point A. At x is equal to 4 feet. So what we will get if you put the value of x in this equation, so minus 2 into 4 is minus 8. So we will be equal to minus 8 kip. And m will be equal to minus 4 square, which is equal to minus 16 kips into feet. These are at C, at point C, because x is equal to 4 feet at C. So V is equal to C and M is equal to C. Okay, now for the region CD and for region CD and just at D minus. Now what D minus shows that? D minus shows that D, it is slightly before this point. Clear? Exactly. We can take this distance as 8, but we will not include this 15 kips load. And what we will do is that we will draw the free body diagram. So free body diagram will be like this. This is the beam from A to C. There is a distributed load of 2 kips per feet. Clear? And from C to D, this is C and this is D. So total distance is 8 feet. Clear? 8 feet. So what we will do is that we will convert this distributed load into a point load. So it will be 2 multiplied by the length over which it acts, and that length is, this length is 4 feet. Clear? This is 4 feet. So it will be 2 into 4 is minus 8 here, and that will act at a distance of 2 from both sides. So this will be 2 feet, and this will be also, the remaining will be also 2 feet. So when you cut it at D minus, so you will be having a shear force which is acting downward V, and you will be having a moment M as well. And at this point is point O. So we'll find this V and M by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So minus 8 which is acting downward minus V is equal to 0. So minus V minus 8 is equal to 0. So from here we will get V is equal to minus 8 kip. Okay. For this moment, we will find the sum of all moment about point O is equal to 0 and taking the counterclockwise moment positive. So first moment is this moment which is counterclockwise. The second one is this 8 into perpendicular distance will be now. This total is 8. So 2, this is 2. So this will be 6. So this will be counterclockwise. So it will be also positive. So I can write it plus m plus 8 multiplied by 8 multiplied by 8 multiplied by 6 is equal to not 8, 8 multiplied by 6 is equal to 0. So what we will get is that moment will be equal to minus 48 and unit will be kips into feet. This is just at D negative. Okay. Now for region DB, I will write here by using another color for region DB and at B negative. Now B negative means somewhere here. So what you will do is that you will cut the beam and you will draw the free body diagram. It will be like this. This is your point A. From A to C you have distributed load. Again the same thing. And this is your point D where you have a point load of 15 kips. Clear? And at point D when you cut it, you will be having a shear force V and you will have a bending moment B. The total length of this beam is now 12 feet till point B. This is 12 feet. This distance is 4 feet. This is 4 feet. And this distance is also 4 feet. Okay. So how we'll find? So first thing is that we will convert this distributed load which is 2 kips. So 2 multiplied by length 4, that will be equal to 8. Clear? And then we will apply the shear force. Then we can find this shear force and moment M by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0. So again you can see 8 which is downward. So minus 8. This minus 15 because it is downward. Minus V is equal to 0. So it means that V is equal to minus 23 kips. And this is just at B negative point. Or you can also say that VB. Now we will find this moment M by using in equation that sum of all moment about point B is equal to 0 and taking the counterclockwise moment as positive. So about point B, one moment is this which is M, that is counterclockwise. So M, the second moment is due to this 15 kips load and perpendicular distance is 15 into 4. This is also positive. So I can write plus 15 multiplied by 4. And the last one is that this 8 into perpendicular distance is now, this is 2, 4 and 4 is 10. So plus 8 into 10 is equal to 0. Okay. Now this M plus this is 60 plus this is 80 is equal to 0. So it means that moment is equal to minus 140 kips into feet. Okay. Now we have all these values. So what we will do is that we will just plot them. Clear? And we will draw the shear force and bending moment diagram. For that I will take this figure and I will copy it downward. Okay, like this. I will make it smaller. Okay. Now for shear force and bending moment diagram, what you have to do is that you have to take vertical lines from the end of this beam. Clear? And first we will draw the shear force. So again horizontal line and X in feet. Here on y-axis you have V shear force which is in kips. Okay. Let one unit is taken as 5. Clear? Or you can also take it as 5. 5 minus 5 minus 10 minus 15 minus 20 minus 25. Okay. Starting from point A, you can see you have shear force V is equal to 0. So your shear force is 0 at this point, clear? And at point C, this is your point C, this is your point D. If you project them, like this is your point C and this is your point D. Okay, at point C, you can see at C, V is equal to minus 8. So what we will do is that we will take minus 8 somewhere here. Okay, and you can see now the shear, the distributed load is a horizontal line with 0 degree and negative. So shear force will be a 1 degree line and its slope will be decreasing. Now, what is the moment shear force at point D? So at point D, you can see that at point D, you have shear force is again this one. V is equal to minus 8. This is for region CD or just before minus D. So V is equal to minus 8. And again, you can see from the first method, from C to D, there is no shear force, so it will remain horizontal till point D. Now, at point D, we have minus 15 kilonewton load. So minus 8 minus 15 will be minus 23. So it will be like here, somewhere here, minus 23. And at point just B negative, which is minus 23. So just B negative, it is minus 23. And at the end, you can see that you have this BY, which was plus 23, which will make it close. And this will be your shear force diagram. Okay. Now we'll draw the bending moment diagram. So for bending moment diagram, you have X in feet, and on Y-axis you have moment, which will be kips into feet. Let what we have taken in this, we have, okay. So what we will do is that due to limitation of space, we will take it minus 50, minus 100, minus 150, and minus 200. Okay. Starting from the first point at X is equal to 0, we have MA is equal to 0. So your first point will be this one. This is 0. At X is equal to C, we have moment is minus 16. So C is this point. So minus 16 will be somewhere here. Let this is minus 16. Now you can see that shear force is a 1 degree line and slope is decreasing. So bending moment will be a 2nd degree curve and it will be like this. Okay. It will be like this. Now, what is the value of moment at point D? So this is, you can see this is the value, which is minus 48 kips. So minus 48 kips will be somewhere approximately here. Okay, now you can see shear force is a horizontal line with 0 degree. So bending moment will be a straight line using joining these 2 points. And the last one is moment at point B, which is minus 140. So minus 140 will be somewhere here. And again, shear force is a horizontal line with 0 degree. And this is negative area. Clear? So what we will get is that we will get a straight line by joining these 2 points with slope decreasing. And at the end, when you will find the reaction force, which we have find over here, you have checked that MB was how much? This is plus 140. So minus 140 plus 140 will bring it to 0. And this will be your BMD, bending moment diagram. So from this SFD, shear force diagram, and bending moment diagram, you can calculate the maximum absolute value of shear force and maximum absolute value of bending moment. So this, you can see this is minus 23, or that is equal to 23 kips, and moment is equal to minus 140 mod, and that will be 140 kips into feet. So this was all about this problem 5.10 that we have solved by using 2 methods. And I hope you have enjoyed both the methods, and if you have any question, you can ask me in comment section. Those who are new to my channel, then subscribe it, and don't forget to hit the bell icon so that you can get notification about my latest videos. For any query, again, you can write me in comment section. Thank you for watching. Back in this video, we are going to solve problem 5.26 that is taken from Mechanics of Material, Beer and Jhonston, 6th edition. So statement is knowing that W is 12 kilonewton, draw the shear and bending moment diagram for beam AB and determine the maximum normal stress due to bending. So you can see this is beam AB having point load at C which is 8 kilonewton and at E it is 8 kilonewton. A weight of 12 kilonewton is suspended uh, through this pulley and this is acting downward. As a result, this rope will exert a force upward which is 12 kilonewton acting on that. And the cross section is shown over here. This is wide flange beam which is W310 by 23.8. So you have to determine the shear and bending moment diagram. So let's start with the solution. So first step is that if you remove this pin support at point A, so you will be having a vertical reaction force which is AY, as well as you will have a horizontal reaction force which is AX. And similarly, if you remove this roller support at point B, so you will replace it with a vertical reaction force which will be BY. There, so we'll find this AX, AY and BY by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force toward right is taken as positive. So AX is acting toward right and there is no other horizontal force, so it means that AX is equal to 0. Now we'll find this another force which is you can say AY. So for that we will take sum of all moments about point B is equal to 0 and taking the counterclockwise moment as positive. So you can see this weight which is acting downward will exert a vertical force on this rope, this rope will exert a vertical force on this beam, and let this force is represented by 12 kilonewton. So now we will apply this equation. So sum of all moment about point P is equal to 0. So first moment is due to this force and perpendicular distance is 1 meter and this is counterclockwise, so it will be positive. So I can write over here that 8 kilonewton multiplied by 1, that is positive. The second moment is produced due to this 12 kilonewton load and perpendicular distance is 2 meter and it is producing clockwise moment, so it will be negative. So I will write minus 12 times 2. The third moment is produced due to this 8 kilonewton load and perpendicular distance is now 3 and this is also counterclockwise moment, so it will be positive. Plus 8 multiplied by 3, and the last moment that is produced due to this AY and perpendicular distance is 4 and it is producing clockwise movement, so it will be negative. So minus AY multiplied by 4 is equal to 0. Okay. Now we will find this AY. So 4 times AY will be equal to 8 minus 24 plus 36, and we will get here is that this will give us plus 12 8 20. Okay, so you can see 8 3 is 24, not 36, so I will correct it. So this will be 24. So plus 24 minus 24 will cancel, so we will get 4 times AY is equal to 8, and from here you will get 8 AY will be equal to 8 divided by 4, which is equal to 2 kilonewton. Now we'll find the last unknown, which is By, that can be obtained by using the third equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So Ay, which is upward, so plus 2 minus 8 plus 12 minus 8 minus 8 plus 12 minus 8 plus By is equal to 0. Okay. So you can see this 8, 8 minus 16 plus 12 is minus 4 plus 2 is minus 2. So By will be equal to 2 kilonewton. Now you have all these reaction forces. So we will able to move to draw the shear force and bending moment diagram. So for that I will take the vertical line from the end of this beam in order to draw the shear force and bending moment diagram. So this is the vertical line. First we will draw the shear force diagram. So for shear force I will take a horizontal line to show length x in meters. And on y-axis we have shear force having unit kilonewton. Let each division is equal to 2 kilonewton. So 2, 4 and 6. Similarly -2, -4 and -6. Okay, starting from point A, you can see at A we have AY which is 2 kilonewton. So I will draw 2 kilonewton. So this will be your first point. Now moving from A to C, there is no other force, so it will remain horizontal till point C. I will make it horizontal till point C. Let this is your point C. Okay. Now you can see at point C we have -8 kilonewton. So 2 minus 8 will give you -6. So shear force will change from 2 to -6. So I will draw vertical line from this. So this is -6. Now moving from C to D, there is no other force. So it will remain same and we will get a horizontal line till this point. But at this point D, you can see you have a 12 kilonewton load. So -6 plus 12 will give you +6 at this point. So shear force will change from -6 to +6. This is +6 kilonewton. Now from D to E, again there is no load, so it will remain horizontal. So from this D to this E, it will remain horizontal. And at point E, you have -8 kilonewton load. So 6 minus 8 will give you -2 kilonewton. So shear force will change from this to -2 kilonewton. This is your -2 kilonewton. And moving from E to B, there is no other load, so it will remain horizontal. And at the end, you can see you have By, which is +2 kilonewton. So it will make this upward to the 0. So from this, you can conclude that you have drawn a correct shear force diagram. Now, we will move toward the bending moment diagram. And for bending moment diagram, you have to draw a horizontal line to show length in meter, x in meter, and on y-axis you have moment which will be kilonewton into meter. Okay, so what we will take is that we will take this one division is equal to 2 there, so 4 kilonewton into meter. Similarly -2, -4, and this is -6. Okay, starting from first point, at first point you have at point A, as x is equal to 0, so moment will be equal to 0. Now the shear bending moment is actually the area under the shear force diagram. So you can see the first area under the shear force diagram is this one, this A1 here, and this A1 is equal to this height which is 2 and the length which is 1. So 2 multiplied by 1 which will give you 2. So first your point will be this 2 at this end. So you will get this point. I will choose blue color. This is your first point. Now you can see that shear force is a horizontal line with 0 degree and bending moment will be 1 degree higher. So it will be a straight line and slope will be increasing because this area is positive. I will draw this vertical line from this, straight line. Now the second area is this area which is equal to A2, and this A2 you can see this is equal to this height which is -6 multiplied by length is 1. So -6 multiplied by 1 will give you -6. Okay, so here we have 2 kilonewton. So 2, this 2 -6 will give you -4. So -4 will be at this point, your bending moment will be this one, -4. And again you can see you have this shear force is a horizontal line with 0 degree, so and this area is negative, so bending moment will be 1 degree line and the slope will be decreasing, so you will get this straight line. Okay, let me join these 2 points. Okay, now the third area is this A3, and you can see this A3 is 6 multiplied by 1 and this is positive, so A3 is equal to 6 multiplied by 1 which is +6. So -4 plus 6 will give you +2 at this point. So you will get the bending moment at this point will be like this. This is plus 2. And this shear force is a horizontal line with 0 degree and A3 is also positive. So bending moment will be 1 degree line and slope will be increasing. So you will get, you can join these 2 points. So you will get this. Okay. The last one is this A4. So A4 is again, you can see this A4 is equal to minus 2 multiplied by this length, which is 1 meter. So it will be minus 2. So plus 2 minus 2 will give you 0 at this point. So again, the shear force is a horizontal line with 0 degree and this A4 is negative. So bending moment will be 1 degree higher and slope will be decreasing. So by joining these two lines, you can complete the bending moment diagram. So what I can write here is that this is BMD bending moment diagram and this is shear force diagram. Okay, this was our first part. Now in second part we have been asked to determine the maximum normal stress due to bending. As we know that maximum normal stress is equal to maximum bending moment mod divided by the section modulus. So you can see here that maximum bending moment, absolute value of maximum bending moment is minus 4 kilonewton into meter mod. That will give you 4 kilonewton into meter. And what about x? Since we have been given that this is W 310 by 223.8. Clear? So from the table, let me show you. I will go toward the table and you will select the W 310 by 23.8. So you have to go to the property of rolled steel in appendix C. So here you will choose the SI units. Okay, so W310. Okay, now you can see here that this is W310, but 23.8 is here. So what you will get is that you will get this Sx, which is 280 into 10 to the power 3 cubic millimeter. So 280 into 10 to the power 3. Sx is equal to 2, wait, Sx is 280 into 10 to the power 3 cubic millimeter. And if you convert it into meters, so Sx will be equal to 280 into 10 to the power 10 to the power 3 multiplied by 10 to the power minus 3 power 3. And this will be cubic meter. So that will give you 280 into 10 to the power 3 into 10 to the power minus 9 cubic meter. And at the end, it will be 280 into 10 to the power minus 6 cubic meter. Now you have both the value, just use it. This formula, maximum bending stress is equal to maximum bending moment, which is 4 kilonewtons. So 4 into 10 to the power 3, it will give you Newton divided by Sx, which is 280 into 10 to the power minus 6 cubic meter. Okay, cubic meter. And this one is Newton into meter. So it will cancel Newton, 1 meter will cancel with that. So you will get 14.29 into 10 to the power 6 Newton per square meter. That will be the maximum, absolute maximum bending stress. So maximum bending stress in Pascal will be 14.29 into 10 to the power 6 Pascal, because Newton per square meter is Pascal. And if you want to convert this into megapascal, so maximum bending stress is equal to 14.29 megapascal, which is the answer of our second part. And that is all about this problem 5.26. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Example 6-1. So statement is draw the shear and moment diagram for the beam shown in figure 6.4a. So you can see this is a simply supported beam that is acted upon by a uniformly distributed load of W. Clear? The length of this beam is L. So let's start with the solution. So first step is that if we remove this support, so there will be a reaction force. Let this is RA, and if we remove this roller support, so we will have a reaction force that is represented as RB. So we'll find this reaction force RA and REB by using equation of equilibriums. Equation of equilibriums. So how? So let's move. And so first equation of equilibrium is that sum of all moment about point B is equal to 0 and taking the counterclockwise moment as positive. So first moment due to force is RA and perpendicular distance is L, and that is producing movement about point B, and this is clockwise. So I will write it minus RA into L. The second moment that is produced by this distributed load, and this distributed load when converted into point load, so it will be W into L, and that will be acting at a distance of L by 2 from both sides. Clear? And that will also produce a counterclockwise movement, and that will be positive. So I will write plus W into L by 2 is equal to 0. I will also show this load, distributed load when converted into point load. So it will be W into L, and that will be L by 2. Now if you solve this, so you will get RA into L is equal to WL square over 2. So from here you will get RA will be equal to WL over 2. So this is your reaction force at point A. Now we will move to another equilibrium condition, that sum of all forces along y direction must be equal to 0 and force taken upward as positive. So you can see we have three forces. One is RA, the second is RB, and third one is W into L. Their sum must be equal to 0. So RA, which is W into L over 2, minus this one, which is W into L, plus RB is equal to 0. So again from here you will get RB minus WL over 2 is equal to 0. So from here you will get RB will be equal to WL over 2. Now you have both the reaction forces RA and RB. So we will move and we will section the beam at any point. So if we section the beam at any point and draw the free body diagram, so for x is greater or equal to 0 and less or equal to L. So if I cut the beam and draw its free body diagram, so definitely here we have RA, which is WL over 2, and we have a distributed load which have magnitude W, and when we convert it, it will give you W, and let this distance is X where we have cut this beam. So it will be W into X, and when you cut it and at any distance, so there will be a shear force and reaction moment. Let this is M, and this is 0.1. So we'll find this shear force and bending moment. So how we will, so first equilibrium condition is sum of all forces about y direction must be equal to 0. So you can see that we have three forces. One is this one, the other one is this one, and third one is shear force. Their sum must be equal to 0. So I will write WL over 2 minus W into X minus V is equal to 0. So from here you will get V is equal to WL over 2 minus W into x. And if you take w as common, so we will have w into L by 2 minus x. This is the shear force equation for the range x is greater than 0 and less or equal to L. Now we'll find the moment. So sum of all moment about point 1 is equal to 0 and taking the counterclockwise moment as positive. So first moment is due to WL over 2 and perpendicular distance is x and it is producing clockwise about this point 1. So I will write minus W into L over 2 and perpendicular distance is x. The second moment is due to this W into x and that will be acting at a distance of x by 2 and it is producing counterclockwise movement, so it will be positive. So plus W into x into perpendicular distance is x by 2 and there is external moment m, their sum must be equal to 0. So from here you will get moment is equal to wx square over 2 plus wx square minus wx square over 2 plus wlx over 2. Again, if you take w over 2 is common, so you will get lx minus x square. This is the moment equation. Now you have both the moment and shear force equation 1. Equation 1 is shear force equation, while equation 2 is bending moment equation. So with the help of this equation, we will draw the shear force and bending moment diagram. I will copy it. And I will paste over here so that we can easily draw the shear force and bending moment diagram. So we'll write equation 1 over here. V is equal to W into L by 2 minus X. So we have both these two equations. So for shear force diagram, I will draw vertical lines from the end of the beams and along horizontal line there will be the length of the beam, so shear force. Now you can see at this point you have a reaction force which was WL over 2 and there is also reaction force which was WL over 2. So at this point at x is equal to 0, or you can simply, you have this equation, so you can put this is equation number 2 and this is your equation number 1. So for x is equal to 0, put in equation 1, we will get V is equal to WL over 2. You can say that when x become equal to 0, so this equation will be WL over 2. Now for x is equal to L by 2. So when you put x is equal to L by 2 in this equation, so this term will be equal to 0. So it means V is equal to 0. So shear force will be equal to 0. For x is equal to L, so put in equation 1, V will become equal to minus WL over 2. So you can put, so you have three values. This one 0 and this one at. So at x is equal to 0, we have V is equal to W. Let this 2 division, this is WL over 2. At x is equal to L by 2, let this is, for example, this length is L by 2 there. So we have shear force 0. At x is equal to L, we have shear force is minus WL over to which is this point. Now you can see that this load is a horizontal load, so shear force be 1 degree higher, and it will be a straight line with slope decreasing. So you can join these 3 points by using a straight line. So this will be your shear force diagram. Now for bending moment diagram, again I have to draw a horizontal line, and here we will take the bending moment. Now for x is equal to 0, put in equation 2. Equation 2 is this one. So when x is equal to 0, so this whole moment will be equal to 0. For x is equal to L over 2, when you put it in equation number 2, you will get moment is equal to WL square over 8. And for x is equal to L, when you put in equation 2, you will get moment will be equal to 0. So you can put and you can check. Now we have 3. At x is equal to 0, we have moment is equal to 0. So this point at x is equal to L by 2, we have a moment which is, let this point is WL square over 8. And at x is equal to L, we have moment 0. You can see that shear force is a 1 degree line and the slope is decreasing. So bending moment will be 2nd degree curve, and that will be clockwise. So I will draw it by using a curve there. And similarly here we have the same scenario. The shear force is a decreasing, 1st degree and decreasing. So bending moment will be a curve, and it will be a like this one. So this was all about example 6-1, in which we have learned how to draw the shear force and bending moment diagram and how to write the equations, that is for shear force and bending moment, and by then using this equation we have drawn the shear force and bending moment diagram. I hope you are enjoying my videos and you are learning from it. Those who are new to my channel, then subscribe it and press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Example 6.12. So statement is the simply support beam in figure has the cross-sectional area shown. Determine the absolute maximum bending stress in the beam and draw the stress distribution over the cross-section at this location. So you can see this is a simply supported beam with a uniformly distributed load of 5 kN per meter. The cross-section of the beam is shown over here. Clear, you can see all the dimension. The width is 250 millimeter. The total height is 300 plus 20 is total height is 340 millimeter. The thickness of web is 20 millimeter, while thickness of flange is 20 millimeter. So you have to determine the absolute maximum bending stress and then draw the shear or distribution over the cross section at this location. So let's start with the solution. So our first step will be, if you remove the reaction supports, so definitely you will have a reaction force. Let this is RA, and reaction force at this point is represented as RB. So we will find RA and RB. So how you will find that? So you will apply the equilibrium condition that sum of all moments about point B is equal to 0, and taking the counterclockwise moment as positive. So about point B, one moment is due to RA into perpendicular distance is 6, clear, and it will produce clockwise moment. So I will write minus 6 times RA, and the second moment is due to this distributed load. This when convert it into point load, so 5 into total length is 6, which will be 30, and it will be acting at the half of length of the beam, which is 6 by 2, and that is 3 meter, and it is producing counterclockwise movement, so it will be positive. So I will write plus. I will also convert this distributed load into point load. So 5 into total length 6 will be equal to 30 kilonewton, and that will be acting at a distance of 3 meter. So 5 into 6 into perpendicular distance is equal to 0. So 6 RA will become equal to 30 and 90. From here you will get RA will be equal to 15 kilonewton. Now you have RA, you can find RB by using another equilibrium condition, that sum of all force along y direction must be equal to 0 and taking the upward force as positive. So 3 force, one is this one, other is this one, and third one is this one. Their sum must be equal to 0. So RA, which is 15 kilonewton, minus 30 kilonewton plus RB is equal to 0. So from here you will get RB will also equal to 15 kilonewton. Now you have this RB, so you will then move toward drawing the shear force and bending moment diagram. Why? Because we know that maximum stress is equal to maximum bending moment into C divided by I. So we need maximum bending moment. That's why we will draw the shear force and bending moment diagram. So you have to draw vertical lines from the end of this beam, and first you will draw the shear force. Okay, so here we will have a shear force in kilonewton. So let each division is 5, so it will be 15. 15 will be here. Clear? So at initial point you have RA, so 15 point will be, first point will be here. Now you can see this is plus 15, and when you want to find the stress due to distributed load, this load, so this will be 5 into 6, 30, and that will be minus because it will be downward. So 15 minus 30 will bring it to minus 15 at the end. So minus 15 will be this point. So you have to join these 2 points by using a straight line. Definitely you will get shear. Now at the end you can see RB, which is plus 15 kilonewton. So this is minus 15, and this will bring it to the plus 15 will bring it to the 0 again. So at this location this will be 3 meter. Your shear force will be 0. Now we will draw the bending moment diagram. So again, for bending moment diagram you will have to draw, this will be X in meter, where you have bending moment in kilonewton into meter. So now your first area is this one. Area under the shear force diagram will give you the bending moment. So this area will be equal to, since it is triangle, so it will be 1 over 2 into its height, which is 15 multiplied by 3, and that will be equal to 22.5 kilonewton into meter. So at the distance of 3 meter you have a bending moment of 22.5. So let each division is of, let's say 5. So this will be 20 kilonewton, and 22 will be in between these two. So you will have a point like this. Let this is 22.5. Since this shear force line is a 1 degree line and slope is decreasing, so bending moment will be a 2nd degree curve and it will be clockwise. So we will draw the bending moment will be like this one. Okay, now you can see that we have this area which is also similar, and this area is, again, this is minus 22.5 when you calculate. So plus 22 minus 22.5 will bring it to 0 at this point. So you will have the bending moment curve will be like this one. So I will draw it. So this is your bending moment diagram. Now from this bending moment diagram, you can see your I will write from bending moment diagram. You have maximum absolute bending moment will be equal to 22.5 kilonewton into meter. So you have this value. What about C? So we will go to C will be equal to, we will go to this section, and you can see this is its neutral axis. So C is the distance from neutral axis to the topmost. So this is C, which is 150 plus this distance. 150 plus this 20, which will be equal to 170. So C is equal to 170 millimeter, and we will convert it into meter. It will be 0.170 meter. Now we have this value as well, but we do not know I. So we will calculate I for this beam. So for that I will copy this and will bring it to this position so that we can easily calculate I. So I, you can see that for I we will find the moment of inertia of this upper flange and this web. So I will write the formula by using parallel axis theorem. So it will be equal to I bar plus AD square, sum of inertias of each element. So we have three. One is this one, second is web, and third one is this one. So you can see the upper and lower plates or flanges are at equidistance from the neutral axis. So we will take only one, but we will multiply it with 2. So 2 multiplied by this plate. Let me clear this. So first thing is that you will take this plate. I have shaded it. So 1 over 12, its breadth is 250 millimeter, which in meter will be equal to 0.250 into h cube, and h for this plate is 20 millimeter. So it will be 0.02 whole cube plus AD square. Now what is the area of this plate? So its area will be 250 multiplied by 20. So 250 when converted into meter, it will be 0.250 into 0.02. This is the area multiplied by d square. Now d square is, if I zoom it, so d square will be from neutral axis till the mid of this. So this is your d. Clear? And this d is equal to 150 plus half of 20, which is 10. And that will be equal to 160 millimeter. So d will be 160 millimeter. So 160 millimeter is actually 0.160 meter, and it will be a square. Plus we have the middle portion. Now you can see the middle portion is this web one, and its moment of inertia will be equal to 1 over 12. This is 1 over 12, not 1 over 2. Okay. So 1 over 12 B. Its breadth is, you can see, 20 millimeter. So 20 is 0.02, and its total height from this till this is 150 plus 150, which is 300, and that will be equal to 0.300 whole cube. We will not use here A plus D plus AD square, because you can see its D will be 0. From its this flange web will have a midpoint over here, and this neutral axis is passing through centroid of this flange. So D will be equal to 0. So AD square term will be 0. So we will only left with this thing. So when you calculate all these values, so you will get I in term of meter will be 0301.3 into 10 raised to power minus 6 meter power 4. Now you have I as well, you have maximum bending moment, and you have C as well. So you can put it in this formula. So you will get the maximum bending stress. So you will write maximum bending stress is equal to maximum bending moment into C divided by I. So maximum bending moment was 22.5 kilonewton. So 22.5 into 10 to the power 3 will be converted into Newton. C was 0.170 divided by I is 301.3 into 10 to the power minus 6 meter power 4. So again, when you calculate it, you will get 12.7 megapascal. So bending stress maximum is equal to 12.17 megapascal. Okay. So this is the maximum bending stress. So if you want to find the stress at point B, let me clear it. So if you want to find the stress at B, so what we will do, you have this formula, stress at point B is equal to minus M into C is replaced with YB, distance from neutral axis to the point B, divided by I. So your maximum bending moment is 22.5 into 10 to the power minus 3. Now your B point is at a distance of 150 millimeters. So you will convert YB is 0.150 divided by I is 301.3 into 10 to the power minus 6. So again, when you solve it, it will be 11.2 megapascal. So this is stress at point B. So this was the extra which I have done because a student requested me to explain this problem. So that's why I'm going to explain it. Now we will do our next part, that is draw the shear distribution over the stress distribution over the cross section. So for that I have to draw the cross section. So let me draw it. So this is the I will roughly draw it. So this is the beam. Clear? You have this beam. Okay. You have okay. So this is the beam, and this is your horizontal axis, and the axis that is outside is this one. Clear? Okay. So this is your neutral axis NA. Now by using this formula, stress is equal to moment into C divided by I. Clear? So you can see that you will have maximum stress when C is from neutral axis to this point. This is your C. So when C is maximum, so you will have maximum stress. Clear? And you will have a maximum stress like this. So this will be your maximum stress. At point B, this was the point B, you will have a maximum stress like this. And at this point you will have zero stress. So it will be like, if I draw it like this one, and here you will have stress. So you will have maximum moment, maximum value over here, and then downward, and at center point you will have zero stress. So stress will decreasing. If I represent it over here, so this will be your stress at Y is equal C at C. So you will have stress like this, and again at this point you will have a lower magnitude stress. So your stress figure will be like this, and it will reduce to, at this point you will have a stress like this, and at this point you will have a 0. So if I represent it like this, so this stress at this point will be equal to 0, and stress distribution will be like this. Again, if I draw it, let me draw it over here. So if you have I-beam like this, so you will be having a maximum stress over here, and then if this is your neutral axis, so this stress will be like this one. So if here top is decreasing, and this point it will be 0, and here it will be increasing. So this will be the stress distribution. I hope so. Also you can see that this is the force, stress distribution force, and it is producing a movement in this direction, because you can see this force is in this direction and it is producing a couple, and this force is in this direction. So it is producing a counterclockwise movement, and this movement will be equal to 222.5 kilonewton into meter. So this was all about example 6.12. I hope you have enjoyed this video. Again, if you are new to my channel, then subscribe it and hit the bell icon so that you can get notification about my latest video. Thank you for watching and supporting me. And if you have any question, you can ask me in comment section. Take care.